Hello, my name is Elena Kim, and in this video, I'm going to be talking about a paper I co-authored with Stephen J. Miller entitled Constructions of Generalized MSTD Sets in Higher Dimensions. I figured the best way to go through and explain the abstract of this paper would just be to go through and explain the title. So we're going to start with the MSTD aspect of the title. So we say a finite set A in the integers is MSTD if for the sum set, which we define to be all the possible sums made of elements of A, and the difference set, which we define to be all the possible differences made from sets of A. We have that the size of the sum set is greater than the size of the difference set. Now you would expect these sets to be pretty rare because addition is commutative, but subtraction is not. In fact, you'd probably expect the percentage of subsets of 0 to n that are MSTD to go to 0 as n goes to infinity. However, in a pretty surprising 2006 result, Martin and O'Brien proved that a small but positive percentage of sets are in fact MSTD. Now I'm going to talk about generalized MSTD sets. So if for the ordered pair S1D2 and the ordered pair S2D2 such that they're not equal to, but we have S1 plus D1 is equal to S2 plus D2, we have the size of the set where A is summed S1 times, then subtracted D1 times is strictly greater than the size of the set where A is added S2 times, then subtracted D2 times, then we say that A is a generalized MSTD set. Generalized MSTD sets were studied by Iyer, Lazarev, Miller, and Zhang in their paper Generalized More Sums Than Different Sets that appeared in the Journal of Number Theory in 2012. They proved that there's a positive percentage of generalized MSTD sets and showed that there does not exist a set A such that the size of Ka plus Ka is strictly greater than the size of Ka minus Ka for all K. Our paper extends this work. Now I'm going to touch on the constructions aspect of the title. So Martin and O'Brien used a probabilistic argument to prove their seminal result that there is actually a positive percentage of MSTD sets. On the other hand, Iyer, Lazarev, Miller, and Zhang made use of constructive arguments. So in papers on MSTD sets, these are the two main types of arguments that you will encounter. Our paper chooses to use explicit constructions of generalized MSTD sets. Finally, I'm going to talk about in higher dimensions. So I mentioned that our paper extends previous work. We do this by looking at the similar results in higher dimensions. So more specifically, in our paper, we look at generalized MSTD sets that are subsets of ZD. Not all of Iyer, Lazarev, Miller, and Zhang's results easily generalize to higher dimensions. Particularly difficult is the result that there does not exist a set A such that the size of Ka plus Ka is greater than the size of Ka minus Ka for all K. The one-dimensional argument that they used relied on showing that for large K, the middle of Ka is filled in, and the growth of Ka is linear in K. In higher dimensions, the growth of Ka is not linear, and certain constraints are imposed on A to argue that the middle of Ka is filled in. So we are able to show that for certain sets, we cannot have the size of Ka plus Ka is greater than the size of Ka minus Ka for all K. Thank you so much for listening to this video, and I hope that you will end up taking a look at our paper.